Thanks, Sue. I'll also be mentioning an Eyre Peninsula case study, I suppose, and we sort of brought two abstracts together for this one, so we've got a lot of co-authors there, and certainly need to mention the support from GLEC, the Agricultural Bureau movement, some of the NRM boards, and Department of Environment and Water in this. I suppose, as we brought two abstracts together, I'll talk a bit about the current and future status of soil acidity, the statewide strategy and actions identified, and the Eyre Peninsula experience. Well, I'd like to start off, I suppose, just talking about critical pH levels. And those of you that, if you take nothing else, just take my critical pH levels home with you and have a look in the garden. So if you're getting pHs of calcium at 5.5, we're getting what we call soils with acidities in the zone. If less than 5, sensitive crops become affected, sensitive microbes and rhizobium affected, acidity starts to creep into subsurface layers. Toxic aluminium and manganese can be released. Once we get to 4.5, I suppose even tolerant crops or acid tolerant crops become affected. And once we get down to 4, we start getting what we call irreversible degradation of the clay component of the soil and release of iron. And I suppose with acid soils, some of the off-site impacts include acidification of water, release of toxic compounds, declining ground cover leading to erosion and salinity. And the causes have been known for a long time, I suppose. They were sort of around in in Europe in the days of the Romans, that soils becoming too acid. But the general causes that we see are nitrogenous fertilisers and some forms of nitrogen fertiliser in particular, those that particularly contain ammonia, and to a lesser things like urea. The removal of products, so as you're taking products out of the gate, you're actually taking alkaline material out, so the more products, the more quickly you'll actually acidify. So it is an issue that's associated with good, high-yielding sort of farming, I suppose. The more yield you get and the more, I suppose, inputs you have to that, the quicker your rate of acidification can be. The third sort of main component of acidification is the leaching of nitrate at the bottom of the root zone. This is something which I suppose varies between soil types and agricultural practice. A shallow-rooted plant will have perhaps more nitrate leaching, and the acid is left behind as the acid is more closely, I suppose, attracted to the soil particles. Just sort of moving on, we've looked, I suppose, through a statewide committee and developed a state strategy, which has looked at the cost of lost production, improved the mapping and extent of, and developed a predictive capacity of where acid soils are likely to develop. We've done quite a bit of work through Giles, looking at monitoring of lime use and liming targets and a lime deficit. Identified barriers to landholders. Why aren't they, I suppose, aware of their acid soils and why aren't they treating them? And also identified a need for a range of other activities such as better understanding of acidification rates and buffering capacities, I suppose the overall nitrogen fertiliser cycle, precision techniques and mitigation techniques, particularly in the low to medium rainfall areas where this is really an emerging issue. Just a little bit on, historically, I suppose where we saw soil acidity was in the map on the left-hand side there, where it's sort of the higher rainfall parts of the state or the higher rainfall cropping zone. The areas in red or orange. There's about 2 million hectares of land there that's considered acid prone, and then we're now starting to, I suppose, predict that over the next 40 years we'll see an expansion into pretty well many other parts of the state, with the orange and brown markings on the map on the right. And I suppose we're expecting that we'll see at least a doubling, or maybe up to 5 million hectares that are now will be acid prone in 40 years' time. It may not be my problem, but it'll be someone's. Now, some of the, I suppose, lime monitoring we've got, I suppose, is to look at. We've actually been able to, through a modelling exercise, develop, I suppose, a model which calculates based on, I suppose, the acid-prone area within an NRM region, and the percentage of those soil types that are below pH 5 now, and superimpose land use. We can actually come up with I suppose, a lime target to neutralise the acidity caused by that farming system. And in the graph here, I suppose, you can actually see that over time, depending which region you're in and the amount of lime going out, you can see a cumulative lime deficit. And some regions, such as like Eyre Peninsula, have seen basically this is a negative positive, I suppose, but we've actually seen that the rate of liming is far below what is needed to require the acidification on that land that's already prone in that region. Northern York and other regions are above that there. And I suppose that's given us a guide as to how well are we sort of going in terms of treating acidity across the agricultural regions. In some of these regions, I said, certainly on the Eyre Peninsula, there was no one liming, I suppose, acid soils 30 years ago, so it's a sort of a new issue in some ways as well. Along with that, as I've talked about before, we're also now seeing a spread into new areas. We've seen acidity develop in York Peninsula, around Malalar. We're seeing patches appear in the southern Mallee, and these are new areas, never had an acidity problem before. And I suppose in the graph on here, we've actually now had to start thinking that, if we're going to have a target for lime, that's actually got to increase over time. And so over the next 40 years, we're predicting that our rate of liming will actually have to go, I suppose, up to compensate for that. And you can actually see I suppose down here, the actual rates of liming versus the target. And you can see last year we actually did do reasonably well. There was a really big increase in liming on Eyre Peninsula, which I'll talk a bit about. The challenge would be to maintain that, I suppose. In terms of what it's costing, we've done some rough estimates of perhaps costing up to $88 million of lost production across the state. And that's really based on looking at the yield response that we get under certain pHs. Also, I suppose, we've developed some monitoring sites now, particularly in the high rainfall areas. We need some more of these. And I suppose this one just highlights over a 9-year period that we're getting a soil dropping from about 5 to about 4.5, and highly significant for the range of crops and the effect of acidity in that time. It's taken 7 years to do that. The soil on Lower Eyre Peninsula dropped about half a unit down to about 30 centimetres, and gone from a soil that was sort of marginal for affecting just a few crops to having most crops would be then affected, I suppose, once you get down to that sort of pH. And we've got about 50 of these sites, so it's mostly in probably the historic areas, and we probably need to develop some more in the lower rainfall areas. Done a little bit of work looking at the buffering capacity of soils, of these new soils that are developing soil acidity, and you've actually, in those same landscapes, you've got calcareous soils, so they've got natural lime all through them. And if you work on an acidification rate in this environment of about 75 kilograms of lime per hectare per year on the farming system, on the right-hand side, you can actually calculate how many years have you got before you'll drop that soil by 1 pH unit. You can see the calcareous soils have got about 6,000 years, so I've got a bit of time on those ones. On the sandy loam of a dispersive clay, which is the second one here, we calculate there's about 30 years there before we might drop that from, say, 6 to 5 pH, so 1 unit pH change. For the carbon levels and the textures, that's what we can calculate out. Thick sand over clay might be 21 years, and on deep sand, about 17 years to drop at 1 pH unit. This is assuming these have been cropped every year and have an acidification rate of about 75 kilos per hectare per year. Another, I suppose, strategy identified for this emerging acidity is the need to understand the distribution of acidic soils as they develop. Historic areas, I suppose, you go and you treat your whole paddock the same and the whole paddock's got a problem. But what we're finding in a lot of these emerging areas that there's just patches of the paddock going out with a problem. And so one of the tools that's been developed and validated in South Australia is to look at precision pH mapping in combination with EC mapping, which gives you some other information on the soil type. And the sort of responses you get, sort of information you get, and this is actually in a dune swale site in Pinaroo. The red areas are actually below pH 5, so they're in that critical acid zone. The blue areas are actually neutral or alkaline, so you can actually see in a dune swale system, and I suppose the EC map on the right-hand side, the red areas picks up the sandier soils, and the yellow and green picks up the flats. So even in what we call a dune swale system, we're now starting to see some of the sandy ridges in that landscape acidify. Just mention that the Eyre Peninsula case study that was undertaken was from a number of projects from various sources, including Department of Environment and Water, NRM and Landcare, and really spent a lot of time quantifying the rates of acidification for that environment, increasing landholder knowledge, introducing tools such as precision mapping and I suppose I haven't shown you, but certainly Excel models to compare limes, conducting a range of workshops and field days, introducing, I suppose, variable lime application, And we've seen a major increase in liming rate, probably almost a tripling, I suppose, in the last couple of years of that. And I should acknowledge Brett Masters from Eyre Peninsula colleague and also Mary Crawford from the NRM board for driving a lot of that. Just a couple of snapshots of that project, I suppose. Some of the results of, again, pH mapping, just highlighting a paddock there where part of the paddock's got a major problem and other bits are actually quite good. And often historically, if a farmer took a soil test, they might actually just cross between those and end up with a mean of that, which might say there's no issue. Or they may have taken their soil test out of the bed a bit and not actually recognised. So again, this, I suppose, technology is enabling them to pick out bits and pieces like that. Some of the other work that Brett was involved in is really looking at trying to better account for what's causing the acidification on farms and using some Excel modelling. I suppose this is an example of that, and I suppose the graph in particular highlights where is the acidification, that system going. He's got a rate over 4 years of between 130 and 200 kilos per hectare per year of lime required to match the acidification, and 46% of that is coming from the program the farmer's using in terms of the nitrogen that's being applied, so the DAP and the urea applied. 27% from the products being taken out the paddock, and 27% from, I suppose, the nitrogen fixation and from some legumes and subsequent leaching of that. So I suppose through this modelling exercise, it's been able to use that and make farmers more aware as well, I suppose, in terms of what's actually driving that acidification. So summary, I suppose, a lime use deficit has accumulated since 1999 and we've seen soil acidity worsening, the areas affected are expanding. While we've seen certainly an increase in lime use in 2017, it's quite encouraging. Much of that was on Eyre Peninsula and we might find that difficult to maintain, particularly as we go into, I suppose, a year following a poor year next year, but we'll see how we go. And we'll need some ongoing efforts to keep and expand that across the state. The soil acidification strategy is identified and is driving the need for better information and science, and we've certainly, I think, done a fair bit of improving some of that. We've probably identified the gaps as well, and this is in turn improving the strategy and how we're targeting various stakeholders and the approach to the issue. And I suppose a lot of this information is actually published on our soil acidity website, which is on the AgX website. I'll leave it there, I think.